Hello, my name is Steve Heald, and I'm going to talk about some of the aspects involved in designing and executing an XAFS experiment. There are many steps involved in carrying out a successful experiment, and we'll consider some of them here in this talk. Some of the initial considerations are that you should really consider: is XAFS the right choice for the experiment? XAFS has its strengths and weaknesses, but if you have, for example, a crystalline sample, maybe some type of diffraction measurement might be better. Also, you might consider, is the experiment feasible? If your sample is too dilute, the element of interest is too dilute, it may be very difficult to actually carry out the XAFS experiment. We'll discuss this in later slides. The other thing is, what is the best measurement method? There's several different ways you can carry out XAFS. We'll discuss that. I'll talk a little bit about making samples and also recognizing some of the issues involved in taking the data. I won't be discussing how to analyze and interpret the data, which is going to be the subject of several other talks in this course. So let's start with discussing some basic facts about X-ray absorption experiments. I like to start with the signal-to-noise requirements. There's three different types of measurements you might be involved in. One would be just mapping the sample to find the element of interest if you're doing a microprobe experiment. In that case, you don't need a particularly good signal-to-noise to see the element in the image. So I assumed maybe a factor of 10 or so for the signal-to-noise would be good. That would, if you remember that the signal-to-noise is the square root of the number of detected counts, that would mean you only need about 100 counts of the element of interest, fluorescence line from the element of interest, per pixel. But you'd have a lot of pixels, so the measurement still might take a long time. For near edge or Zane's measurements, you'd like to have a signal-to-noise better than about 100 to see the main features. So that would put you in the range of greater than 10,000 counts per point. But there's maybe 50 or 100 data points in the Zane spectrum, so you still need a fair number of points to complete the measurement. The more difficult experiment is the extended X-ray absorption fine structure, the XAFS. In that case, you definitely want a signal-to-noise greater than about 1,000. Ideally, you'd like maybe 10 to the fourth. So that means you need more than 10 to the 6 counts per point, and you have at least 100 data points, maybe more, in the XAFS spectrum. So now you're getting up in the range of 10 to the 8th, or even more total counts to get the whole spectrum. Now, it's also important to remember that these are lower limits, because if you don't have a perfect detector, there's going to be background associated with the signal. And that's going to lower the effective count rate, because the noise is going to be the square root of the total signal, not just the square root of the element of interest. So I'll talk more about this in a later slide. So let's talk about some of the methods for measuring XAFS. We'll start with transmission measurements. So a typical setup would use ion chambers to measure the beam. You'd have an I0 ion chamber, the sample, and then you'd measure the transmitted beam. Now what we're measuring is going to be the absorption coefficient. That's what we want to measure for XAFS. So it's always going to be accompanied by the thickness of the sample. So we measure this mu t. And so if we invert this absorption equation, we say that mu t is equal to minus the log of I over I0, or we often plot the log of I0 over I. That's going to give you this mu t. If the sample's thick enough or thin enough that you still have signal after I, we can have a reference foil, for example, a metal foil. This will check the calibration of the monochromator, make sure that it's not drifting with time. Using statistics, just calculating from statistics, the best mu of t to get the best signal to noise, you'd end up with about 2.6 from UT, and I0 would have about 24% of the absorption of the beam, total beam. Now, because of other issues, thickness effects, which I'll talk about in a minute, the practical optimum for a concentrated sample, one where most of the absorption is from the element of interest, you'd want to have a mu-T of about 1.5 would be good. And it turns out that the signal to noise that you calculate from statistics is not very sensitive to this I0 absorption. So anything in the 10 to the 30% range would give you more or less the same signal to noise and be good. Now, because we're measuring current and not counting photons, at some point we're going to be limited in signal to noise by the electronics that's used to amplify the current. And it turns out that for typical situations, this noise will probably limit you to about a signal to noise ratio of about 10 to the 4th, which is good. It's equivalent to having about 10 to the 8th photons that are absorbed in the ion chambers. So if you have a typical beam of 10 to the 10th photons per second, you see that like a 1 second or so measuring time should be sufficient to get a signal that's going to be mostly limited by electronics rather than the number of photons. One thing to note about ion chambers is once we're up to a few nanoamps, that means we're in the range of 10 to the 8th photons per second. The electronic noise should become the most important factor, not the statistics of the number of photons. So if we're running at a few nanoamps, we're probably going to be more limited by electronic noise, not statistical noise. There could be other sources of noise, for example, noise from the beam line, for example, if the monochromator is vibrating or something, but it's not necessarily from the incident flux limitation. The other thing to note about ion chambers is that they tend to become nonlinear at about 10 to 20 nanoamps per centimeter length of the chamber. This is just something I observed for several different types of ion chambers. So for a typical ion chamber that's 15 centimeters long, that means when you get up to a few hundred nanoamps, you have to start worrying about nonlinearities. Particularly, it's easy to get, for example, with an ID beamline, it's easy to get into the microamp range, for example, if you're not careful. And then you can expect the ion chambers to start to become fairly nonlinear. So you'd want to use a thinner gas, such as helium, mixed in to reduce the total signal. So now I'd like to mention a little bit about another way of measuring the transmission, so-called quick XAFS. That's where you continuously scan the monochromator and record the signal on the fly. The nice thing about this is it reduces overhead, so it makes maximum use of the photons, because in typical step scanning, you have to move the motor, wait for the motor to get to the right position, and maybe wait a little bit for things to stabilize. Whereas with the quick scanning, there's no real overhead. It turns out that with specialized monochromators that have a cam or piezoelectric drive, they would permit scanning as fast as a few milliseconds, full XAFS in a few milliseconds, if there's enough incident flux to support that kind of measurement. A direct drive motor, which is probably a little bit more common, this is where you have a large DC motor running the main axis, can easily scan in the 1 or few second range, which is often the necessary time frame to get good XAFS anyway, because there's just not enough counts in a few milliseconds to get the full XAFS range. So this is mostly for transmission, and as I mentioned, it's ultimately limited by the number of available photons. It could be used in fluorescence, but if the fluorescence signal is not very strong, then the signal to noise is going to be limited by the short counting time. Although it could be still quite useful for measuring XANES in fluorescence fairly quickly. This just shows an example of some data that we took at a bending magnet beamline where the flux is somewhat limited. So if we measure fairly quickly 25 milliseconds per point, we get essentially the same data as the step scan at 1 second a point, except there is somewhat more noise in the data at higher K, just due to the limited flux that we had. Another issue with quick scanning is that the typical ion chambers don't have a fast response. So if you're trying to do a few milliseconds a point, the ion chamber may not have stabilized its signal at that time. This shows an example where the green curve is a specialized ion chamber that has a special mesh to improve its time response, and the purple curve is basically a standard ion chamber. So in a standard ion chamber, you have both electrons and ions being collected as part of the current, and the ions travel quite slowly through the gas, and so they take a while for them to reach the collection plate. And so if you have a fast change in the signal, it takes a while for the ions to catch up. So the special ion chamber uses a mesh, a special extra mesh in the ion chamber that can be biased to eliminate the ion current and just measure the electrons at high speed. Okay, so a little bit more about ion chambers. I think all of you will be introduced to this Demeter program package, which includes this program called Hephaestus, and it has a tab there that you can use to calculate the absorption in ion chambers. So for example, if we're at 9,000 EV, we have 15 centimeter long ion chamber, we used nitrogen gas, it's going to absorb about 9%. So that would be a reasonably good choice for that energy. The other thing you can do is if you measure the current and then you put in the parameters for the ion chamber, from the current you can calculate the number of photons per second that's in the beam. So sometimes that can be useful also. Okay, now I want to talk about thickness effects, which could be quite important when you're doing transmission type experiments. So a thickness effect occurs when some part of the beam makes it through the sample or past the sample without feeling the absorption from the element of interest. For example, if you have a pinhole in the sample, or if somehow the beam is going around the sample, or another common factor is if there's harmonics, higher energies in the beam, they'll go through the sample without being affected by the edge of interest. So I just calculated an example here. If we assume there's 5% leakage, this was just for an iron foil, a little more than 2 absorption lengths thick, and we had, say, a hole in the sample that allowed 5% of the beam through, you can see it's quite significantly distorted. You can see that the amplitude of the XAFS is quite reduced, and the edge step is reduced. You can also kind of see here that as the sample gets thicker, the effect is bigger. So the reduction here of the oscillations is greater than the reduction of this near edge feature. So we just take this data and use it to extract the XAFS. We find that just 5% leakage in this case gave almost a 25% reduction in the XAFS amplitude. And if the sample was thicker, this would be even a bigger factor. In fact, iron foil is kind of a good case because typically you'd have other elements around that would also be increasing the total absorption length. So the thickness effects can be calculated, and I just show some calculations here for the different cases. Now, the two cases are different because in XAFS we normalize the XAFS with the edge step. So both the XAFS oscillations and the edge step are distorted. So typically it's partially cancels out some of the distortion. But you can see the case we were talking about is around 2 absorption lengths, a little more than 2 absorption lengths, and 5% leakage. You can see we're getting this roughly 75% amplitude now. And in the Zanes, you get similar effects that's even worse in some sense. So this is a reason why even though the optimum sample thickness is like 2.6 absorption lengths, you might want to operate a slightly thinner sample for concentrated samples, because then you're being less sensitive, much less sensitive to these thickness effects. As I mentioned, one of the problems causing a thickness effect is the harmonics in the beam. This is shown here for a typical double crystal monochromator. We have two crystal reflections. So if we're using the 111 monochromator, this is the throughput through the if we have both crystals. And if they're perfectly aligned, you see the 111 reflection, but you also get the 333, and there'd be 444, 555, which I didn't plot on here. But you can see that the 333 intensity is quite significant compared to the 111. If your synchrotron is putting out higher energies at this energy, then you could have quite a bit of leakage just from the monochromator harmonics. Now, one way to get around that is to detune the two crystals. So we misalign them. In this case, I show a strong misalignment. This is cutting the beam down in half. But now you can see the 111, and this is, you notice this is times 100, so the 333 is basically eliminated. So in this case, you'd have a fairly pure beam. And the other thing to note is that if you do a lot of detuning, you do change the energy resolution of the monochromator somewhat. So if your energy resolution is important, and you want to, you're comparing different experiments at different times, you might want to try to have the same detuning. Now, a somewhat probably better way to reduce the harmonics is use a mirror, they call harmonic rejection mirror. I show an example for just a silicon dioxide mirror at 5 milliradians. You can see the reflectivity has a strong function of energy, and at a certain critical energy, right here, the reflectivity drops off dramatically. So if we adjust the mirror angle such that it's reflecting the fundamental, but you're past the critical energy on the harmonic, we can reduce the harmonics a lot. And just for future reference, typical mirrors are rhodium, platinum, silicon. This shows you the critical energy of the mirror if you divide by the angle of the mirror in milliradians. So if it's 67, well, we can go back to the silicon dioxide standard. Silicon dioxide is very similar to silicon, so 5 milliradians divided by 32 into 32 is roughly 6 keV, which is what this shows. Now, at some synchrotrons, the energy drops off fairly rapidly. The intensity drops off fairly rapidly with energy, so the harmonics maybe are less of a factor. But at a high energy ring like the APS, there's a lot of harmonics. I show an example here where to measure the harmonics, what we did was we put a tin foil in, which has an edge at 29,200 EV, but we scanned the monochromator at 1/3 of that energy. So if there's any harmonics, any third harmonic in the beam, we would see the intensity drop when we go through this tin edge. So here, this shows some data. So if we fully tune up our beamline, there's quite a significant drop in the signal after the tin foil. However, if we detune the monochromator, these are the blue and the green curve, we can minimize quite a bit this change in intensity as we go through the edge. But the best method was to use a harmonic rejection mirror. Then we don't see any evidence for the third harmonic. So why is this important? Well, the thickness effect can be pretty significant. This shows a rhenium sample, which has a pretty strong white line, so it's kind of sensitive to the thickness effect. So the edge step was about 1.5. This has been normalized here. So that means that in the peak here, the total absorption is more like 3. So if we tune up the monochromator, we get, or use the harmonic rejection, we get the red curve. But if we tune up the monochromator, so we have a lot of harmonics, you can see we get the green curve. So there's a lot of distortion in this white line. So coming back to the sample thickness again, this XAFS program is nice for calculating the sample that you need, the thickness of the samples that you need. So this shows an example for YbCO superconductor. This is the formula density. And so if we're interested in measuring a copper edge in this superconductor at 9 keV, we can use the program to calculate how thick the sample has to be for one absorption length. It turns out to be 8.2 microns. But that's the total absorption. If we wanted like one absorption length at the copper edge, we would need 24.8 microns of sample thickness, which actually might be a little too thick in terms of minimizing thickness effects, because that would mean the total absorption is going to be about 3 absorption lengths. And also the program is it calculates the milligrams per square centimeter that you would need to get this absorption. So if you're making a sample, this is a very useful number to have. Then you know how much weight of sample per square centimeter you would need. So now we're going to move on to fluorescence detection. So this again shows a sort of schematic of how you might set up the fluorescence measurement. So you'd have an incoming beam. Typically the sample will be at an angle so you can get the fluorescence out to the fluorescence detector. Most likely you'd want to use the sample at 45 and the detector at 90 degrees, because 90 degrees minimizes the scattered background. And then if there's anything left, you can still measure the transmission and have a reference sample. But if the sample is too thick now for the reference, another approach that is useful is to have a scattering, say a thin foil of Kapton or something, and have your reference sample here. The edge will be a little bit distorted when you measure it in this method, but it's still quite a good method for checking for shifts in the energy with time. Now, if we have a thick sample in fluorescence, by thick I mean basically no beam is getting through, this is what we'd actually be measuring when we measure the fluorescence. So the mu prime is our measurement if we divide the fluorescence signal by I0. So mu is what we're actually trying to measure. So but because it's a dilute sample, the mu is accompanied by absorption of the matrix. So the total absorption, mu t, is this mu plus the matrix absorption. So this is what we'd measure if we just take the ratio of the fluorescence to I0. We have this mu that we're trying to measure in the numerator, so that's good. But we also have the total absorption down below, which, remember, incorporates this mu also. So this will cause some distortion in the actual measurement. And I discussed that a little bit more on this slide, where we look at some typical cases for the measurement. So in this case, I've just assumed that sine theta and sine phi are 45 degrees, because that's our usual case to minimize the scattered background. So if we have a dilute sample, so now mu is very much less than the matrix absorption from the sample of interest, then we can approximate this total absorption by just the mu of the matrix. So now the fluorescence over I0 is directly proportional to the absorption that we're trying to measure. If we have a concentrated sample, however, now mu is almost the same as mu of the matrix. For example, if we had a foil, they'd be the same. And so we have mu over mu here with this other term. And this other term is actually fairly small compared to the total mu. So these two terms will almost cancel. And you'd find that there's very small XAFS in the spectrum. This is called self-absorption. So you can measure a concentrated sample if you have a thin one. In that case, the fluorescence over I0 is, my laser pointing going again here. The fluorescence over I0 then would be, again, proportional to mu. Another case that can be employed for a concentrated sample is to put the sample near 90 degrees, perpendicular to the beam, and then have your detector at a very small glancing angle relative to the surface sample. In that case, the sign of phi becomes very small, and this matrix fluorescence term starts to become very large because it's divided by a very small number of sine phi. In that case, your signal again becomes almost proportional to the absorption you're trying to measure. So I mentioned self-absorption. So this shows what happens if you try to measure a concentrated sample in fluorescence. I'll show a couple cases here. So for the copper metal, this green curve is for copper foil measured in transmission. So that's the data we're trying to get at. And then a sample is made using different thickness powders, which is kind of equivalent to making thicker and thinner samples. And you can see when the powder gets fairly large, we try to do fluorescence, the signal drops off dramatically. Another case is rhenium near-edge data that I took. In this case, it was pretty much a concentrated sample of rhenium, pretty much no transmission. And the black curve is what we actually measured. The red curve is what we thought was in the sample. And if we assumed an infinitely thick sample of this composition, we were able to correct the data and kind of verify that that's really what was there. And this correction is built into this Athena program that you'll be getting lectures on later. So I mentioned this effective counting rate in that first slides. If the fluorescence sample is accompanied by a large background, which it almost always is because the sample, the signal of interest is dilute, is from the element is dilute. So you're going to get scattering and maybe other kinds of fluorescence from other elements in the background. So if we have the signal that we're trying to measure is this N, and we have a background, I call it NB for background, then the signal to noise, if we have a detector, it just measures everything and doesn't discriminate between the two signals. The signal to noise will be the square root of that total counts. So that's this square root here. And we can break that down into the square root of n times this factor. So the square root of n is what we would get if we were able to measure just that fluorescence counts without having the background. And so you can see the signal to noise is this factor larger, 1 plus the NB over n larger. So that means the effective counting rate is smaller by the same factor. So in a typical case, I'll show some examples. 1 millimolar of iron has a background of, say, 20 times this. So this is a very significant reduction in the effective counting rate. Now, we can use detectors to try to just detect N and not detect the background. So a solid-state detector is one way. You'd probably be familiar with that, a germanium or a silicon drift detector. It can have very good background discrimination, so it can eliminate a lot of the background, but they are limited in the counting rate, total counting rate. So if there's a huge background, a lot of that total count rate the detector can handle will be taken up by the background. So you might have a still fairly small counts for the signal of interest. There's other types of detectors, the so-called Lytle detector or the filter or slit detector, where we put a filter in the beam and then use slits to minimize the fluorescence that comes from the filter itself. They can have really large collection efficiency because we can make a very large detector, for example, a large area ion chamber, but they don't do as good in eliminating the background. So I wrote a paper a few years ago, this is the reference you can look up, where I tried to compare different performance of different detectors using this idea of the effective counting rate. So there's 3 types of detectors that we can consider: the filter slit, which I mentioned, the solid state detector, or if you really want to get good energy resolution, And good background discrimination, we can have various types of crystal analyzers which Bragg reflect the fluorescence but reject the background. Now, if all those detectors collected the same solid angle and had sort of typical performance, this is what you would get in terms of the normalized effective counting rate. What I've done is I've normalized the effective counts to the counting the signal to noise you'd have if you had perfect detector N. So if it's 1, that means it's perfect. So a solid state detector, when the background is low, pretty much has a perfect discrimination of the background, and you'll get the full possible counting rate. As the background increases, there'll be some overlap. There's always a small overlap of the background with the signal of interest, and so it starts to drop off. You can see then at some point the crystal analyzer, because it has better background, but it doesn't collect as efficient usually. This is kind of a typical efficiency. You'd have to go to really large backgrounds before it would beat out the solid state detector. Now this was assuming equal solid angles for all the detectors, but typically, as I mentioned with the filters, you can collect a really large solid angle because you're not really limited on the detector size. So say a typical case might be you get 5 times the solid angle with a filter and a slit system than you might with a solid state detector. And because the crystal analyzer is Bragg reflecting, it's really hard to collect a large solid angle unless you have multiple crystals. So I just assumed a sort of a fairly typical case that it's going to be 10 times, be like 10 times, the filter would be 10 times more than the crystal analyzer. So in that case, it's a little bit different here because the normalized counts is to the maximum solid angle signal. The solid state detector is down by a factor 5, so it's only getting 25% of the normalized effective counts that you'd get with the filter and the slit when there's very little background. But again, the solid state is better at rejecting the background. So when you get up to like 20 or 30 times of the signal in the background, then the solid state is better. And typically it's better for the whole energy range. So just to show some examples, as I mentioned, with iron, if you have about a 1 millimolar sample in water, now the background, because this polarization effect eliminates the background when you're right at 90 degrees, but for a real detector, you have to collect angles away from 90 degrees, so a larger solid angle. So as you increase the solid angle, you'll increase the background. So for sort of a typical case of using a filter and a slit, you might collect 10% of the total solid angle. You'd have a background to signal ratio of around 20. Now an example I show below, this is copper in solution. It's 55 micromolar, so it's quite a bit more dilute. We're using a solid state detector, so it only collected maybe 1% of the solid angle. We measured a background to signal ratio of about 200. And another kind of typical case maybe in terms of, say, a microprobe or something, if we had 34 parts per million arsenic in glass with a 2% solid angle, we measured about 25 times background to signal. So let's go back to this copper example. So this is, I used a vortex detector, a solid state detector, but if I don't use the energy resolution of the detector, just look at the total signal from the detector, you can see without any filters or anything, basically we can't see the edge. There's all kinds of other contamination in the beam, so we can't really see an edge. If we put a filter and slits in, and we measure the total signal, we do get quite a bit of improvement. But if we look at the copper, just the copper signal from the vortex, even without the filter, we can now see the edge because the detector is rejecting a lot of the background. But if we combine then with the filter and the solid state detector, we actually get the best signal because we've reduced the background significantly. So even if you're using a solid state detector, if we start getting to really high dilution factors, you might want to consider also using a filter and an appropriate collimating slit. So the issue, now I've talked about fluorescence and transmission, the issue comes up should we use which mode? From statistics, if the edge step of the element of interest is less than about 0.1 or maybe 0.05, depending on the conditions, fluorescence is almost always better. But there's some other factors that might come into this. Monochromatic glitches, how well they're normalizing out. Sometimes they'll normalize out better in the fluorescence for fairly concentrated sample because you don't have much background. How uniform the sample is, that could affect the transmission sample more than the fluorescence typically. If there's other fluorescence lines in the sample, so if you have a lot of background fluorescence from other things that are in the sample, that might change where you'd want to do transmission or fluorescence. And if there's difficult to make a thin sample, as I mentioned, sometimes it's hard to make a thin enough sample and you end up doing fluorescence on a fairly concentrated sample. So yeah, you don't always have to just choose one or the other at the start. You can, if the sample is thin enough, you can do both and choose the one that looks the best at the end. So let me now just fairly briefly discuss some other types of measurements for measuring XAFS. So an electron yield is one way. So there we're measuring the electrons that are given off by the sample as we go through the edge. The electron yield can be easier measured in vacuum or in helium. It's sort of the typical detector, as I shown below. This is what you can purchase as part of the LIDO detector system. The sample is actually in helium atmosphere, and that has some advantages because when the electrons emitted from the sample go into the helium gas, they can generate more electrons. So you typically get a gain in the current of maybe 50 or 100 times compared to just measuring the electrons from the sample in the vacuum. Now the electron yields, because the electrons have a hard time coming out of the sample, it's pretty surface sensitive. For the total yield, it might be measuring the top 100 nanometers or so. Because you're only measuring the top 100 nanometers, it's equivalent to having a very thin sample. So even though you have the same type of formula for the electron yield signal over I0 as for the fluorescence, in the electron yield case, the short mean free path of the electrons means the signal is always going to be nicely proportional to the mu. We don't have this self-absorption effect. So that's why it's a nice method to measure a concentrated sample that you can't make thin enough for absorption and has a lot of self-absorption in fluorescence. So that's what I mentioned here, thick samples, thick substrates where we can't do transmission. It's also very good for low energies, such as, say, the sulfur edge, where the samples for transmission have to be very thin and it's really hard to make it a good sample. It can be used a lot for thin films, especially at low energies, like oxygen edge or carbon edge. And it can enhance the signal from surface layers. So if you have say a film sample where you may want to try to enhance the contribution from the thin oxide layer that's on the film, electron yield could be a good choice. It's not a good choice for dilute samples since there's no background discrimination. So you'd always see the total signal, not just the signal from the sample of the element of interest. Another technique that's often employed for thin film type samples is to measure at small angles. Now, if we just go to small angles, the signal is increased by this 1 over sine theta because the absorption as it penetrates the film is increased. Disadvantage is you can need a fairly small beam or a large sample. because the beam will start to spread out when you go to small angles. There is a special case, as I mentioned, in terms of that harmonic rejection mirror. If you go to small enough angles on the sample, we can actually reflect the beam if the sample is nice and smooth, as is often the case on thin film samples, say that are grown epitaxially. And then we can have total reflection. You can either measure the reflected beam, or you can measure the fluorescence signal in that case. And the X-ray penetration when you're in this reflection mode is strongly limited, even more than this 1/sin theta factor. In fact, the penetration would only be typically a few nanometers when you're reflecting from the surface. So this is a method that you could use, say, again, as I mentioned, that example where you have maybe a monolayer or so of an oxide film on a regular, on a metal substrate, for example, and you could really enhance the surface layer by going to the reflection mode. Okay, so now I'd like to kind of switch gears and talk about actually making the samples themselves. Again, the concentration is of interest, whether you want to do transmission or fluorescence. So if you're trying to do a fluorescence sample, then it's a lot easier usually to make samples. You can just make a large, thick pellet, for example, not worrying about how thick it is. You might need to measure, say, samples at low or high temperatures. That might affect how you're going to try to make the samples. There could be other considerations. For example, if the sample is air sensitive, you need to have it in some kind of containment. The same thing if it's a hazardous sample, either chemical hazard or maybe a radioactive sample. And so remember that the containment, you'll have some windows or covering films. That's going to increase the background absorption. So that could be an issue, especially at lower energies where the containment might be a big contribution to the absorption. So just look at some typical particle sizes now. So I don't know if you're familiar with these meshes that come with the sieves. So if you make a fine powder and you want to get the fine component of the powder, you typically would run it through a sieve. And this table just shows how big the opening are for different sieve sizes. If you've ever worked with a sieve, you know when you get a sieve size larger than 400 mesh, then it starts to get really hard to get the powder through the sieve. 400 is fairly straightforward if you grind the particles very fine, but once you start getting to higher meshes or trying to get smaller particles, it starts to become difficult. One reason is that the fine particles will tend to stick together. So even if your average particle size may be 10 microns, they may be clumped together and then you just go through the sieve. So, but even 400 mesh, you can see that's 37 microns. But if you want mu x of 1 for these concentrated samples, you can see if you're trying to measure the sulfur edge in pyrite, you would like to have the particle size actually significantly less than 1 absorption length because you want to try to get a uniform layer. So 1.3 microns, that's going to be hard to make up particles that size. And it, again, for low energies like oxides, it's pretty much almost impossible unless you have some type of nanoparticle method for making a sample. Even for iron edge and iron oxide, we're still in many microns, or several microns, and of course, ideally, we'd like to be a fraction of that. So all of these are showing that if you have just a 400 mesh particles through a 400 mesh, they're probably going to be a large fraction of those particles are going to be too big to make a nice sample that won't have a thickness effect. So one method that's part of this XAFS school is to use sedimentation to get fine particles. So you grind up the sample. You'll have a mix of fine and larger particles. Then you suspend the particle in a suitable liquid, one that's not going to react with the sample. and allow the particles to settle out. Now, of course, the large, heavy samples will drop out very quickly, and the fine particles will stay suspended in the liquid. So you can draw off, after a certain time, you can draw off the liquid, let that liquid dry out, and you'll be left with the very fine particles. So this just shows a sedimentation time for a particular case of acetone and this density of particles. You can see that if we want to get a few micron particle size, maybe 1 or 2 microns particle, that they would take of order 100 seconds before they would settle out, whereas the larger particles are at less than 1 second. So by just suspending the particles in the liquid and just waiting maybe 30 seconds or so, you could get quite fine particles in the liquid and draw that out. So that's a nice method for getting fine particles. It is a little tricky and can't be used for everything. Another method which I quite like, it's worked very well in the past, is to rub the powder onto a tape substrate, so sticky tape. For example, so-called Scotch Magic tape works very well, or Kapton tape. You have to be a little careful with Kapton tape. You can buy it with 2 different kinds of adhesive. You want to get the version that has the acrylic adhesive. The adhesive that's sort of standard for the Kapton is designed for high temperatures and includes, I think, chlorine and silicon in it, so it's quite absorbing. Anyway, if you say get a 400 mesh powder, which is fairly fine but still has some larger particles, and you rub it onto the tape. The trick is not just to rub it on, like once or twice, but to vigorously rub it into the tape. Maybe spend 30 seconds or a minute rubbing it on the tape. What that does is the rubbing can break up any clumps of particles, so it spreads out the particles. And also, what you'll do is you'll rub off the larger particles. They'll end up off the tape if you rub it enough. So I've found that in the past, even with the 400 mesh powder, if you rub it onto tape, you can usually get much finer average particle size on the tape. And then you'll usually find, at least for the higher energies, 10 keV or so, that you'll need several tape layers to get a proper absorption length on the sample. So because you have several layers, you end up with a really nice uniform sample. Now there are some disadvantages. The single layer on the tape may still turn out to be too thick. This would particularly be the case if you have if you're trying to measure something lighter like sulfur. So one layer might still be too thick, or if you're measuring something heavier like 20 keV or something, you may find that you need a lot of layers to get a good sample with the right edge step. If there's too many layers, then the tape may start to be a problem with the absorption. But it's typical, like for, say, those superconductor samples, the yttrium YBCO, that maybe you would take 8 layers of finely ground particles on the tape would give a nice sample. So then you'd end up with a really nice uniform sample. You should look out for, I mentioned the Scotch Magic tape. It does work really well for making the samples, but it does have a small amount of titanium, so you have to be a little careful if you're trying to measure something close to titanium. But there's other tapes that could be used. You might have to experiment a little with them to see what works. A very common way of making samples is pressing it in pellets, because it's nice. You can weigh out the sample, and remember that Hephaestus program would tell you how much weight you need per square centimeter, and then you can press a pellet of that weight and you have about the right amount of sample in the beam. Now, because the sample has to be very thin, typically, you might have to use a binder to get a pellet that's going to hold together. So you'd want to use something that's fairly light, low Z material. Graphite, boron nitride, or even things like plastic powders have been used. The graphite and boron nitride are good if you need to heat up the sample, but there's other binders that can be used. You might want to mix the binder and the powder together in a ball mill or something to make sure they're uniformly mixed. And then just press it into a self-supporting pellet. Again, though, you got to remember, just because you have the right weight, you still need very fine particles, powders. If you have a mix of fine particles and larger particles, say you use the 400 mesh, there might be some particles that are 20 or 30 microns thick. When you put them in the beam, very little of the beam is going to make it through those particles, but they'll incorporate a large fraction of the weight of the sample because they're large particles. So what you'll find is if you make a pellet of that type, is that you'll calculate that the delta, the mu x step would be, say, 1, but when you measure it, it's going to be something lower, maybe a half or something. That's because part of the sample is in those large particles that aren't going to contribute to the transmitted beam or the absorption. So you have to be still have to be careful to get a very fine particle. Finally, I'll just briefly mention a couple other methods for making samples. You can cast the sample in something like epoxy or Duco cement. It's similar to making a pellet, but you're casting it. You have to be a little careful, though, that they're compatible, the chemical compatibility between the samples. For example, we made some of those high TC, the YBCO samples in epoxy. They were okay for the first measurement, seemed to be okay, but when we came back a few months later and measured the same samples, we found that they had changed. They had actually reacted very slowly with the epoxy. The picture just shows an example. These are actually cross sections of filters that were made using powder in Duco cement, but you could use a similar method for making samples. A method that sometimes is used, you could capture the very fine particles that is suspended in liquid on a filter paper. As long as you're careful on how you filter it, it can be quite uniform. You may need to still stabilize the sample by, covering it with tape or something, so that when you handle it, the particles aren't lost. But there can be other methods of making samples. The main thing is to get the right thickness and the right uniformity. Now, one issue that can come up when making samples, either from particles or if they're actually single crystals, it's possible that you can end up with samples that are unintentionally oriented. For example, if the particles are, when you grind them up, are platelets, which might happen if you have a asymmetric crystal structure, then when you rub them onto tape or press a pellet, you may partially orient them. The plates may tend to align with themselves. And that can make analysis of the data difficult because you don't know exactly what the orientation is. So if you suspect something like that might be happening, a good test is to measure the sample at different orientations. Just rotate the sample in the beam and make sure that the signal is the same. And this is also actually a good way to check for these thickness effects. If you suspect that there might be some problem with the sample thickness, as you rotate the sample, you'll be changing the sample thickness, and if you get the same result for two different sample thicknesses, you can be pretty confident that you don't have a distortion from thickness effects. Now, if a typical case is you might have a sample that's asymmetric, for example, has a large c-axis direction, but in plane it's more or less the same. And if the sample's aligned, typically that might happen that the c-axis might be more or less perpendicular to the sample surface. Then in that case, if you measure at 54.7 degrees, then the contributions from the in-plane and out-of-plane signals will be the same. So you'll get a signal that's similar, or basically identical, to an unoriented sample. If there's a asymmetry in the A and B axis as well, then this method won't necessarily work. It's only going to work for, say, in plane, out of plane. You might have to spin the sample as well. I just mentioned a little bit about micro XAFS. That's becoming more and more of interest. People measuring in the microprobe. So in that case, we usually end up wanting to have thin sections because if the beam will penetrate into the sample, it can degrade the apparent resolution. So if you have a 1 micron beam, but it's penetrating 10 microns into the sample, then you're not necessarily measuring a 1 micron image of the sample. Also, you have to remember that the beam can see parts of the sample that maybe aren't visible optically. So if you're looking at, the thin section, what you see on the surface, maybe not what's right underneath. There is a method called confocal detection, which I'm not going to go into detail, but if you use special optics on your detector, then you can make a confocal measurement where you're only looking at a certain depth in the sample. Typically, that can have a 1 or 2 micron resolution with the best optics. So you could have a virtual thin section where you just measure a 1 or 2 micron thick region of the sample. One thing I find a lot of users don't realize is when they make their thin sections, they have to support them on something, and typically they put them on a glass slide. But glass has many impurities. Regular glass has many impurities. Arsenic is very common. Iron is very common. And this can really interfere with the measurements. So if you're using glass, it's best to, even though it's more expensive, is to get a few silica slides, which are basically pure SiO2. Another issue with micro XAFS is that the radiation damage can be much enhanced by the concentrated beam. I'll show an example in a minute. For XAFS measurements, it can be really difficult in a micro beam situation. For example, if you have a 2 micron beam, but your particle that you're trying to measure is also only 2 microns, to get a 10 to the minus 3 change in the absorption or the signal, say if you're measuring fluorescence, the beam only has to move by like 2 nanometers during the measurement. So as you're scanning the energy, it's really hard to keep the beam position from moving a little bit. And so what you'll often find trying to do micro XAFS is that the Zanes will look okay because you're not scanning the energy very far, and also the Zane's structure is a stronger feature in the beam. But when you try to do XAFS, you start to see these funny backgrounds that make it really hard to do XAFS. So I just caution people, it can be a difficult thing to measure the full XAFS on the microprobe. It's not impossible, but you need to look for areas where the signal is fairly uniform, areas that are somewhat larger than the beam size. Just to get back to this radiation damage issue, even without the microprobe, say on an insertion device beamline, or even on a bending magnet for really sensitive samples like biological samples, you can get radiation damage, which means the beam is changing the sample. This is really a problem for wet samples. So if you have a wet sample, not even a sample in solution, but just a sample that's still moist, the beam can interact with the water, generate free radicals, generate hydrogen or OH ions, which can react with the sample. So one way to minimize that is to freeze the sample. Even wet samples that are frozen tend to be much more resistant to radiation. You can have if you have a sample in solution, you can have a flowing solution, so you're refreshing the sample before it's damaged. You can run fast scans, so this is where this quick scanning may be of interest. You can run a fast scan on a small region and then move the sample and do another quick scan before the sample has a chance to damage in that small region. Another method is to have some type of spinner, say, on the sample, so you're spreading out the area of sample that the beam is hitting at any one time. So just so some example, that I ran into fairly recently. I was measuring micro XAFS on technetium. This is for a waste management problem. So we were looking for technetium pertechnetate, which has this edge feature, this pre-edge feature, and comparing it with technetium-4, which doesn't have that feature. So we're trying to figure out what was the ratio of pertechnetate and technetium-4. And so this, because you can see the data was a little noisy, I measured multiple scans to try to get better data. So the blue curve in all these cases is the first scan in a set of scans, of typically 6 or 8 scans. And then the green curve is the last scan. And I did not normalize these edge steps. So these are the measured edge steps. So you can see what's happening, say in this case, is the edge step has dropped. So we've lost technetium from the beam. Somehow it's migrating away from the beam area. And it turns out that what we're losing is the pertechnetate part of the sample. So you can see we've lost this pre-edge feature here. So the pertechnetate is apparently much more mobile and for whatever reason moves away from the beam. And you can see that in various cases here. So the one sample which didn't have any pertechnetate didn't show any real radiation damage. So this is just an example of what can happen. It's always good to look out for radiation damage by measuring multiple scans and maybe not measuring one really long scan, but measuring several shorter scans. Another issue is when measuring single crystals is you get Bragg peaks. So we're scanning the energy of the beam, and if you have a single crystal, at some point the energy will be right for one of the Bragg peaks to be excited in the sample. So what this does is, in the worst case, the Bragg peak could come into your say, fluorescence detector and saturate it. But even if the Bragg peak doesn't come into the detector, because the beam is going in and then coming back out, it can excite more fluorescence. So in other words, the beam enters, but it comes out, and in both paths it can excite fluorescence. So you end up with these spikes in the data. This shows the case. They're trying to measure a monolayer of iron, 2 monolayers, on gallium arsenide single crystal substrates. And they had a lot of Bragg peaks. So they tried rotating the sample a little bit. You can see you can move the Bragg peaks around. And one method is to measure it 2 different angles and then try to splice the good parts of the spectrum together. That gets to be a little tricky, but can be done. Another method, which doesn't always work for all samples, but it's quite effective, is to spin the samples. So this shows I had these epitaxial grown thin films on single crystal substrates. So they give a lot of Bragg peaks from the substrates. But by spinning the sample, and also you got to remember that the Bragg peaks that come towards the detector are going to be elastically scattered peaks. So they're going to be at a different energy than the fluorescence. So by spinning the sample, even if a Bragg peak comes into the detector, it only comes into the detector for a very short period of time, so it doesn't really saturate the detector. So by spinning and using a solid state, say energy diversity detector, it's a very effective way to pretty much eliminate Bragg peaks. So that's pretty much what I wanted to talk about today. I just have a few final thoughts before I close. As I think I've tried to show, is that good sample preparation is really essential for success. You need to have the proper thickness, the proper uniformity. So it's important to plan ahead before making the samples. And using those programs such as XAFS, you can run some simple calculations that can be really instructive. It can also help you to determine how difficult the measurement will be. For example, you could calculate for a very dilute sample what fraction of the beam will be absorbed by the element of interest, and you might find that the measurement time will end up being very long. Just a comment, from my experience, it's generally better to collect good data on fewer samples than rushing through many samples. The problem at using synchrotrons is you usually only have a couple days of beam time, and you have a lot of samples that you want to measure, so the temptation is to try to get through all the samples, but then you have, say, reduced quality data on a lot of samples. That can turn out to be difficult to analyze and difficult to interpret the data. So I think it's just good practice, if possible, to try to make sure you get good data before you move on to the next sample. You may have to have more than one run then, but at least you'll have good data. And just sort of the final thought is the XAFS amplitudes, I think, that I've shown, are the most sensitive to all these distortion factors. You can usually get the bond lengths fairly well, even on a poorer sample. But if you want to get good XAFS amplitudes, you need to have a good sample. So there's thickness effects that can affect that near edge, and XAFS, there's self-absorption if you're doing fluorescence. And so if you're trying to measure good amplitudes, for example, you want to get good coordination number or compare different samples, you should try running some of these simple checks that I mentioned, either measuring samples at different thicknesses, maybe rotating the sample and measuring at different angles. So that's what I had to talk about today. I hope this information was useful, and thank you for listening.